This is Chapter 4, Example 8. Steady state operating data are provided for a compressor and a heat exchanger in the figure below. The power input to the compressor is 50 kilowatts. So remember, when power in, that's actually negative, right? So this is power from our compressor, and that's going to be the negative 50. So just remember that. As shown in the figure, nitrogen flows through the compressor and heat exchanger with a mass flow rate of 0.25 kilograms per second. The nitrogen is modeled as an ideal gas. A separate cooling stream of helium is modeled also as an ideal gas with a K value of 1.67. Also flows through the heat exchanger. Stray heat and kinetic and potential energy are negligible. So determine the mass flow rate of helium. So looking at this, we're going to have to decide our system, and I'm going to put a boundary around our system here. So that's our system. It contains both the compressor and the heat exchanger. And we can see we have two inlets, one for the nitrogen going in, and one outlet for the nitrogen. The other one between the compressor and the heat exchanger is within the system. And then leaving the system is helium leaves at the exit 5 but enters at inlet 4. Okay, so let's put together our engineering model. And for this, our known. So we have nitrogen is compressed in the compressor and then exchanges heat with helium in the heat exchanger. Okay, we need to figure out what we're going to find, and we said that earlier was the mass flow rate of helium in kilograms per second. And then we have to come up with our engineering model. And one thing that we noticed that we can look at nitrogen and helium as an ideal gas. Another part of our engineering model was we look at the steady state mass balance. We have to look at the mass balance. And so our mass balance, recall, is dmcv over dt. Is if at steady state, that is equal to 0, right? And so because this is also equal to our masses, we have two separate, our gases don't interact at all. So we have two separate ones. We have mass 1, where nitrogen, and it goes in one inlet and goes out one out exit. So that's true, right? Because this is the sum of masses in minus the sum of masses going out. And then our helium, mass of helium is going in one inlet and one exit. So that's true for our mass balance. And then we also have to look at our energy balance at steady state. And recall at steady state for energy balance here at dt, that is equal to 0. So we're going to set this equal to 0. And recall that's internal energy or with flow work. And so we put that together as our enthalpy, our kinetic energy, and our potential energy. So one thing that was mentioned in the problem already, that no stray heat was transferred. So QCV is actually 0, and potential and kinetic energy are going to be 0. So if we put in all our terms here, right, this is our entire energy equation, and then we're going to apply our assumptions, right? Heat is 0, and we said kinetic and potential energy are 0 in each one of these cases. So recall, we have to take an account for every inlet and every exit. So if we simplify this down, that's what we get here. We have our work, and we'll bring this over to the other side, and that is the mass of our nitrogen and the enthalpy difference, and the masses of our helium with their enthalpy difference. And we have our border. Okay, so we got our boundary around our system, and we're trying to find our mass flow of helium, right? That's what we're trying to find, the mass flow of helium. And that will be, right, 4 or 5. So we're going to try to solve for M4. All right, we want to solve for M4, so I'm going to bring that on the other side. So M4, I'm going to bring that onto the other side. I'm going to switch the order of my enthalpies because the negative sign comes in. And then we got negative work plus M1, H1 minus H3. To simplify this a little bit, we said that, right, helium is an ideal gas with a value of K. So when we look at H5 minus H4, our enthalpies, if we do the ideal gas model, we know that Cp is equal to T5 minus T4. And by definition, Cp is, I'm going to use the universal gas law, is R times K, K minus 1. So if I stick that in there, I got H5 minus H4 is equal to R, K, molar mass, K minus 1, and it's T5 minus T4. I'm going to stick that into here. M4, as you know, I like to solve for my variable and then stick everything in. So now I have to divide, whoops, there's a plus sign here. Okay, now I have to divide everything by this value here. So that's what I'm going to do. So M4 is going to be equal to, and this comes over on this side, and so this is going to be flipped, molar mass, K minus 1, universal K, and this temperature is on the bottom, and that is going to be multiplied by, all right, so values that we need. Well, molar mass I can find, R I know, K is given in the problem. The two temperatures are given right here in the problem for 5 and 4. They're 175 and 25. The work is given in the problem right here. Right, this is going to be minus 50 kilowatts. Mass, and I was very negligent here. Mass of our nitrogen is given in the problem, so I have M1. And so I need H1 and H3. And I look here and I see that this is an ideal gas. So I'm given pressure and I'm given temperature. And so we're going to look at a table. And this is for the ideal gases, right? We have 280 Kelvin. And we're looking for H. And so H is right here. 8141. So H is here in kilojoules per kilomole. Okay? 8,141. Okay? Now that we have H1, we have to find H3. And that is at 350. Go to that same table. 350 is down here. 10,180. So now we just need to put all our values in. So we're going to do this. I might run out of space with all the unit changing, but we'll see what we can do here. All right, so M4 is, we have our molar mass, which, let's look at this table here. Molar mass of air, okay, is 2897 kilograms per kilomole. Universal gas constant, we have 1.67 minus 1, And remember, the difference in Celsius is the same as the difference in Kelvin. So 175 minus 25 is 150 Kelvin. So Kelvin cancels. Kilomoles, we got kilograms over kilojoules. And then here we have a negative 50 kilowatts, which is a kilojoule over seconds. And then we have our mass, which I'm going to divide by molar mass so that I could get rid of the moles here. We have here 0.25 kilograms per second over 28.97 kilograms per kilomole. And then we have here, right, I'm continuing on. I need to go down here. And we have H1 minus 10,180, and that is kilojoules per kilomole. Let's cancel some of our units out here. Like I said, we have Kelvin cancels here, kilomoles cancel, kilowatts cancel, so I have kilojoules per second. And this one, kilograms cancel, kilomoles cancel, so I have kilojoules divided by seconds, which is what we want. And because then that's going to cancel out our kilojoules are going to cancel here, and we're going to get kilograms over seconds. So when we solve for M4, we put our values in, we should get a value of 0.04095 kilograms per second.